Okay, I think we are ready to start. Welcome everyone to the ITMP seminar. And today we are happy to have Congkao Wen, and he will speak about integrated four-point correlators in closed force Young Mills. Please start.
Great. So first, I'd like to thank Dimitri for inviting me. So I will talk about integrate four-point correlators in this particular CLA and for Young Mills. So this is work I did with Daniel Dolagoni from Taiwan and Michael Green. He has a joint position at the Queen Mary and Cambridge. I think they are both in the audience. So the talk will mainly based on this recent paper. We also summarized some of the main points or main results in this short letter. Okay. So I think it's fair to say that the correlation functions in enforceable Young Mills have been a subject of interest for many, many years, especially since the discovery of ADS-CLT correspondence. So let me say briefly, the correspondence says that a quantum gravity in the zeta space is equivalent or dual to a conformal field theory on the boundary. Then the physical observables, such as scattering amplitudes in the zeta space, is equivalent to the correlation functions in the dual conformal field theory. Okay. So one of the best studied example of ADS-CLT duality is that on one hand, we have type 2B superstring theory on the background ADS5 cross S5, whereas on the other hand, we have this standard quantum field theory, namely four-dimensional and for Young Mills, which is a conformal field theory. And there's some ADS-CLT dictionary where in particular it says alpha prime expansion of the string amplitudes is mapped to large N expansion of the conformal field theory correlator. So in particular, the alpha prime goes like 1 over square root of N. And the string coupling or string complex feather coupling, which is expectation value of the complex scalar, which build out the axion and the dilaton, now is identified with the Young Mills, well, again, complexified Young Mills coupling, which contains the theta angle and the G Young Mills. This is a known fact that both theory, type 2B string theory and enforceable Young Mills, has this beautiful SL to Z modular symmetry. So which takes coupling in this form where A, B, C, D are integers and which has determinant 1, namely AD minus BC equal to 1. So I already said a little bit that we will consider the complex feather coupling. So in the case of the Young Mills theory, they are the theta angle plus 1 over G Young Mills square. And in the case of string theory, they're going by expectation value of axions, and the G string, where G string is basically expectation value of dilaton. So this SO to Z duality in the language of string theory, it's often called the S duality, whereas in the field theory or enforceable Young Mills, this is called the Montolo-Oliver duality. And this is one of the main topics we would like to study in this talk. So this duality, when you choose properly A and B, C and D, you can see that the duality relates weak coupling and strong coupling. Therefore, to study such a duality, it's necessary to compute observables such as amplitudes or correlators at the finite coupling. To compute anything non-trivial at the finite coupling in general is very hard. So in the case of superstring amplitudes, it was known for a while now that at least for the first few orders, in the Lorentz expansion or alpha prime expansion that the amplitudes are known to all orders in the string coupling. I will briefly review what are they. And so our aim is to try to study the other side of the ADS-LD duality, namely study correlation functions in enforceable YAMLs, again, for finite coupling. Clearly, it's difficult. The idea was that instead of computing the correlator itself, one can compute so-called integrated correlator, which I will define shortly. And in the larger N expansion, at least for the first few orders, actually the thing as the first few orders in the string theory, that from the integrated correlator, you can reconstruct the full correlator, reinstall the space-time dependence, and we will see that the result matches precisely with the expectation from string theory. So this is a story at the larger N limit, but as I was trying to emphasize, the integrated correlator is interesting on its own, especially in this talk, we will in fact emphasize this integrated correlator at the finite N and the finite coupling. Just to comment, so from ADS-LT duality point of view, the study we are doing, we are doing in particular to explore this SO2Z duality. Not only you have to look at the finite coupling, we also have to go beyond the supergravity, because SO2Z only start to play role when you turn on alpha prime expansion, only after you turn on alpha prime corrections. So in the language of duality, especially for the non-perturbative effects, we are matching the YAML's instanton effects with the d-instanton effects in the string theory. Okay. So here's a outline what we will discuss today. So I will review some general property of 4-point correlation functions or superconformal primary operators in enforceable YAMLs. Then I will introduce this integrate 4-point correlators in enforceable YAMLs, and in particular emphasize how this is computed from supersymmetric localization. After we set up the computation, we will present a representation of at least one of the 4. So there are several of, well, at least 2 of them. We will present at least for one integrated correlators in a very elegant way. And this formula we will present is a conjecture. So we will at least derive it for SU2 case. And for more general N, we will study it, say, in various limits. For instance, finite N, we will study weak coupling expansion, so small coupling expansion. So this will be like a loop expansion. And we will compare this loop expansion result with known results in the literature. And indeed, we will find match. And we will further study larger N expansion with small default coupling and large default coupling, and just to study its property. Again, so some of the results will match what's already known in the literature. And finally, we will study larger N expansion at the finite coupling and the finite theta angle. So this will make a content about this string amplitudes I mentioned earlier. Well, indeed, so that's what I'm saying here. Finally, I will conclude and make some remarks about the future directions. Okay, so what is the object we want to study? So we want to study 4-point correlation functions of superconformal primary operators that build out those 2 scalars. So, and for super YAMLs, it's a YAML's theory contains gauge field, but because of supersymmetry, it also contains fermions and scalars. This scalar transform under SO6 asymmetry or SU4 asymmetry. However, it's convenient to get rid of this SO6 index by contracting it with a kind of polarization vector we call y, which is now vector. So to make it now is to basically to subtract the trace part of this operator. And the trace part is so-called a Konichi operator, which is non-BPS. So said in another way, this operator we're studying here is a BPS operator. It's protected by supersymmetry, and it has a conformal dimension 2, and 2, no matter if you turn on the quantum collection, so 2 is protected. And in particular, is for the correlator, 2-point and the 3-point correlators of this operator, again, are protected by supersymmetry, that in the sense that they are computed by weak contraction. So things become interesting, or the first non-trivial case is where we have 4-point correlators, and it's convenient to write these 4-point correlators into a 3-part, which again computed by weak contractions. Then the remaining part I called I and T, where I is a factor which I won't even write it down, that is fixed by the symmetry of the theory. So this is sometimes called the partial renormalization theorem. And what's the remaining part, in some sense, is the dynamic part, and that's what we will be focusing on. Okay, so this is a function of cross ratios U and V, and it's depends on the rank of the gauge group. So here we will just study SUN theory, and it also depends on the coupling. So I will write as a complexified coupling tau. Great. So what has been known about this correlator in perturbation theory? This was known up to 3 loops due to the work of Drummond and his correlators. And in the planar limit, the integrand, so not integrated result, was constructed until 10 loops. Another important effect about this correlator, which will be relevant to us, is that the first non-planar contribution turned out enters first at the 4 loops, not 2 or not 3, only first entered 4 loops. So perturbation computation, I think, it was most efficiently done in a way using so-called Lagrangian insertion. So the idea was that if you have L loop, or say 1 loop, this will depend on coupling. Then if you take a derivative with respect to coupling, that will bring down basically a Lagrangian. So therefore, roughly speaking, L loop contribution to this 4-point correlator is associated with a L plus 4-point tree-level correlator with L Lagrangian inserting. An important observation is that in particular, when this is the chiral Lagrangian, in fact, the answer is independent on you choose a chiral Lagrangian or Lagrangian. And then important observation is that this O2 and the chiral Lagrangian actually on the same multiplier. Then there's a so-called hidden permutation symmetry between those operators. Using exploring that property, this was power enough for them to construct the integrand up to 10 loops. Very impressive. The other direction which I and my cooperator has been interested in is to explore, say, exact results of this correlator, exactly in the sense, not doing perturbation. We want to study this correlator for arbitrarily finite coupling, but in the larger N expansion. For that, until now, so the result is known up to sub-leading in the sense, when I say sub-leading in the sense compared to the supergravity limit. And translated into string language, this is basically an order of D6 out of the 4 in the alpha pi expansion of the string. And this result, as I will briefly review, was derived from integrated correlator at the very end of this talk. Okay. So in fact, let me actually show the result, but we would come back to this later. So one useful technique is to write the correlator instead of as a function of cost ratios U and V, but instead it's convenient to write in Mellin space. So basically, you do a Mellin transformation, and for very good reasons, we remove some of the gamma functions, and this remaining object is called a Mellin amplitudes. And this Mellin amplitudes in the large N expansion, as I mentioned already, so here C is basically the so-called central charge, so related to N in this way. So large N expansion or large C expansion, we found that the correlator takes this simple form. So the first term is the supergravity contribution. Again, I will come back to this later. So this term is actually R to the 4. This is a supergravity at the one loop. Then this is D4 R to the 4. This is D6 R to the 4. Anyway, those functions are so-called non-holomorphic Instanton theories. And this one is so-called generalized non-holomorphic Instanton theories. And the important message I want to deliver here is that those functions contains both perturbative and Instanton terms. Okay. So one of the goals of this talk is try to reproduce this formula, but certainly we will do more than that. Okay, so as I emphasized, so we are interested in the correlator for arbitrary coupling and arbitrary N. In particular, because we want to study the modular SL2Z symmetry, and we will turn on to use this powerful technique from supersymmetric localization. So let me briefly say the idea. So say you have a action, you want to do partial integral, and you can deform the partial integral by some deformation which depend on t. Okay, and if the deformation, well, so first of all, this is the symmetry of the action. Second, if the deformation obeys this condition, it's easy to see that turns out that the partition function will independent of this deformation t. So therefore, we can compute this deformed partition function at any value of t. In particular, t equal to 0 is the one we wanted to compute. This is the one we start with. Or I can compute the same thing at t equal to infinity. Well, at t equal to infinity, the partial integral is dominated by delta v equal to 0. So therefore, for a theory like this, the partial integral is localized to submanifold where the field space obeys this condition. For certain theories, this submanifold is even finite dimension. That's the case for the NQ2 star superYAMLs. So again, let me remind you, so we want to compute correlation functions in N4 superYAMLs, but let me start with a different theory. It's called NQ2 star superYAMLs. First of all, I want to compute the correlators on N4 superYAMLs on flat space R to R4. Instead, let's begin NQ2 star superYAMLs on S4. Okay, so NQ2 star superYAMLs is related to N4 superYAMLs deformed some mass term. Okay, some detail is not important, but so this is a mass term, at least explicitly here. Well, obviously, when I take n to 0, this will reduce back to N4 superYAMLs. Okay, so the information is that I deformed the theory with some mass term. And as I already mentioned, that for this theory, people can do a localization computation, as I mentioned, and compute and reduce the partial integral, to finite dimensional integral. Okay, for a theory or SUN theory. And so again, so because I introduced this parameter mass, so the partition function will depend on mass and of course depend on the coupling. Okay, there are two contributions. One coming from perturbation. So I denote it as Z perturbative. And another one is non-perturbative contribution coming from instantons. Okay. So to be concrete, the perturbation term is given by this so-called bonus G function. So it's explicitly given here. So gamma is the Euler gamma. And the instanton term contains instanton and anti-instanton, where instanton I can conveniently write it as a sum of say k instantons. Okay, great. So again, try to be explicit. So instanton contribution takes this, maybe not well, I don't know, maybe not so simple form, but anyways, this is an expression for the k instanton contribution to this partition function. And there's a contour integral you have to do, and the contour is surrounding this object called phi I at this particular pole, where R and S is indicated by the position of a box in a Young diagram. So I gave one of the first and non-trivial example is where you have two instantons, say in a SYM theory, where the number box is related to the number instanton. So in the k equal 2 case, you have two box, and you basically distribute this two box in m position. So in the case of SYM, so you can put the two box at the same position, one way like that, the other way like that, or they can be distributed at a different position. So you can generalize this for k instanton. In general, doing computation of this contour integral is very difficult. And as we will see, for the purpose of computing correlation function, something dramatically happens. Okay, so first of all, I should point out there is no localization for the correlators because this procedure I just said introduced this symmetry doesn't work. However, you can integrate the correlators. So that's where it comes from. Integrate the correlators from the partition function due to the work by Binder and his collaborators. Here, I just introduce one out of this actually three integrated correlators. So this is a case where we take two derivatives with respect to mass. That's why we started with N2 star theory. I can introduce this mass operator. So then I can take a derivative with respect to mass. And further, you take one derivative with respect to the tau bar. So that's one of the complex coupling, and take a derivative with respect to tau. And set the mass equal to 0. That allows you to go back to N for super Yamir's. Okay. So let me say a little bit in detail. So when you take a derivative with respect to mass, again, because I introduced this mass term, so you bring down the operators associated with this mass term. And when you take a derivative with respect to, and those operators integrate because they're coming from the Lagrangian, they come from the action. And then you take a derivative with respect to tau, and then you bring down two additional operators. They actually sit on the south pole and the north pole of the sphere. So therefore, this has something to do with 4-point correlators. But as we said, this partition function was defined on S4. So, but I'm interested in the correlator on R4. So you have to do a conformal map that brings you from S4 to R4. Furthermore, by taking derivative, I actually bring down a lot of bunch operators, which eventually related to the one I want to study, called O2, by say supersymmetry or superconformal symmetry. So one has to use supersymmetry and superconformal symmetry to relate all those different kinds of operators or correlators to this one. After you've done all those, you will find that the procedure of taking this 4 derivative will relate it to the correlator integrated over this particular measure. And so here R and the theta is related to the cross ratio. Great. By the way, so feel free to stop me if there's any questions.
Sorry, could you please like reiterate this thing? So tau, like this T curly, is the correlator, right? And G is what you call integrate correlator.
That's correct.
And this G is for some reason simpler to compute with.
Which compute? Sorry. Oh, simple to compute.
Simpler to compute with localization. That's what you're saying.
That's correct. Right. So clearly, the correlator itself, which depends on the cost ratio, so or space time, I cannot compute from the localization because, well, basically, it depends on space time position. It's not invariant under the symmetry. So one cannot compute it from localization. The idea is that when you integrate it over the space-time coordinates, then the localization procedure can work. And so here, for this particular choice of the measure, well, said it another way, of course, I began with this object where I take a 4 derivative with respect to the partition function. Then, I figured out, well, not I, they figured out that doing this 4 derivative with respect to partition function, basically you bring down a bunch of 4 operators. And so this will give you a bunch of, say, 4-point correlators, may or may not different from this guy, but nevertheless, you can do a supersymmetry or superconformal symmetry transformation to relate all of them to the one you are interested in. And doing all those things together, you will find that there's a certain measure. So this measure is coming out from all those procedures. So in summary, take the original 4-point correlator, you integrate it over this particular measure. That's related to the taking derivative with respect to the say Paston or Nikolsov partition function. Okay.
Thank you.
So there are other type of integrated correlators where you can take derivative with respect to other type of parameters. For instance, you can take a 4 derivative with respect to mass, then set the mass to 0, or you can take a 2 derivative with respect to mass and take 2 derivative with respect I call B, where B is the squashed parameter of the. So well, in this case, I started with S4, but the partition function for squashed S4 also known, and B is the squashed parameter. Well, in this talk, I will just focus on this one, but I will briefly comment on the other ones. So let me say the results for this particular one. So first of all, the perturbation term for S02 is more or less straightforward to compute. Sorry, let me just come back slightly. Well, basically, you take this definition for the perturbation term. So if you're interested in perturbative, you can set Instanton part to be 1, and this balance G function has a simple expansion, say in small mass. And for SL2, this is 1-dimensional integral. And you can try and find that the perturbation term is given by this 1-dimensional simple integral. So this is not the straight came out from that 1-dimensional integral of the matrix model, but anyway, it's equivalent. I take this simple form. And the y is basically 1 over g m square. Okay. So this formula, then you can do a small, say, large y expansion. Large y expansion, basically small g m expansion. So it's really the perturbation expansion. So from this formula, first of all, you can infer, say, all loop or the expansion for this integrated correlator. Or you can do a small y expansion, which would correspond to large G-amuse expansion. So I call strong coupling expansion. So you got this 2 formula, which looks may or may not interesting to you.
What about question?
Yeah.
What about convergence of these expansions?
Right. So I will comment on that. Yeah, I will comment on that. Okay. Yeah, I will comment on that. I think well, they are asymptotic, but Bohr-solvable. So this is asymptotic, as you can see, there's a gamma 2s over gamma s, so it's close. But because of this alternating sign, they are Boole Sangobo. So yeah, as I said, these two formula looks innocent, may or may not be interesting to you. The observation we had was that for some miraculous reason, well, I think it's a SO2Z modular invariance, that these two expressions actually can combine together and form the perturbative term or the non-holomorphic Iceland series, which I mentioned earlier. Now, let me introduce this main player. So non-holomorphic Iceland series defined as a say two-dimensional lattice sum, just like this. So here we just sum over integers, and again tau is a complex factor coupling. Tau 2 is the imaginary part, which is related to 1 over g mu squared. And people know quite well about this function, especially understand the Fourier expansion of this function. Fourier, in the sense, expanding this as a Fourier mode around the tau 1. So tau 1 will be related to the theta angle, namely related to the Instanton counting. So this function contains, particularly, two perturbative terms, which take this particular coefficient, and Instanton terms. I even didn't want to bother you. The point that if we go and check these two perturbative terms match precisely, well, with up to overall factor, match precisely with these two perturbative terms I just said. So therefore, as I emphasized, this large Y expansion and the small Y expansion actually can combine and form Iceland series. That leads to us a conjecture for a complete integrated correlator for SO2, and we say, instead of just this Y or GR mu's, we believe that they combine together form this a complete function, now include both perturbative term and Instanton terms with this particular coefficient. Again, so this sum is formal. This sum is not convergent, so I always use Tiku. So by construction, this object matches with the perturbation term because that's how I guessed this formula. So now the next thing we have to do is to check whether or not the Instanton part actually produce the correct answer you would compute explicitly. So I have to skip this detail since I even didn't tell you, but I will just say how you would compute it. First of all, one Instanton computation, for those familiar with this localization computation, actually it's quite easy. Again, in this case, it's a SO2, it's a one-dimensional integral. Actually, you can do that one-dimensional integral explicitly for one Instanton. And the answer you will get is this so-called complementary Euler function and this, this simple expression. Now you can explicitly check if I show you this Instanton sectors, indeed that match exactly with this formula. As for the K Instanton, as I mentioned, the computation in general, K Instanton in the localization for arbitrary K is rather complicated. However, for us, we were just really interested in K Instanton when you expand in small mass at m square order, right? Because we want to take two mass derivative and set the mass to 0. First of all, this function is even in mass actually, so therefore this is a leading order in the small mass expansion. For this object, we proved in our previous papers that only a particular set of Young diagrams contribute. That simplifies the story dramatically, in fact. In particular, we found that only so-called rectangular Young diagrams. So these are the set of diagrams which rectangular, which is a P row and the Q column, such that the P times Q is K for K Instanton. So once we know that, and that allows us to make computation for arbitrary K. And again, once you did the computation and we can come back, compare with this expression, and we found again a perfect match. Okay, so indeed I didn't show you the detail, but I just to assure you that it turns out this expression we kind of guessed by looking at the perturbative term turned out to be correct, even non-perturbative. So in conclusion, we have a complete expression for this integrated correlator in the case of SU2. And that is expanded in terms of this non-holomorphic Iceland series. Now we can do a simple step by write this non-holomorphic Iceland series in terms of Schwinger parameterization. So we introduce one little integral and write this as a Schwinger parameterization. And then you can do this Sum. And that sum, so you may notice that sum has a converged radius at t equal to 1. However, we can extend it. And then we got the final answer in this nice representation. So first of all, I highlight in color. So this object, when you sum over this lattice, two-dimensional lattice, by construction is SL2Z invariant. So this part is more or less like a nice object to have SL2Z invariant. And then we have this additional rational function. So in some sense, the dynamic part is contained in this rational function. So we like to generalize this to SUN clearly. So again, I won't bother you with a lot of examples. So we studied a lot more examples, and that allows us to make a conjecture that for SUN, again, the integrated correlator take exactly the same form I emphasized for SU2 case, and the only change is this rational function. Now I call it BNT. So it's a rational function of t depend on n. So that rational function has this particular form where the numerator q is a polynomial of degree 2n minus 1, which is explicitly given by here. So you may notice this looks not a rational function because the argument depends on 1 minus t, but it is a rational function. If you plug in any value of n, can verify this is a rational function. Indeed, one can prove that this is a rational function to write this in a different form. Well, this function looks a bit random. However, sorry. Okay, before that, let me make a few examples. I will come back to this. So this function looks a bit random. However, this is a very interesting property. So let me make some examples just for you to get some idea how they look like. So indeed, for SL2, I already show you. It's a function like this, and for SU3, it looks like that. So one thing you notice that it's a symmetric polynomial. So the first term and the last term, and in the middle, in fact, this is generally true. And this is symmetric polynomial property, and the right power in the denominator make this inversion invariance property of this rational function. So this will play important role when we really study this correlator. Although I won't bother you with the details, but I just to mention that these two property turn out to be important when we really study this correlator. Again, so I gave a presentation as a lattice sum. On the other hand, you can also write this as just like in the case of SO2 as expansion in terms of Iceland series, non-holomorphic Iceland series. Again, so for arbitrary n, so there's a constant, then there's a sum or expansion in terms of Iceland series with a coefficient. And this coefficient is basically can be computed from Bn, this rational function. So said in another way, this rational function is the generating function for this coefficient if I expand this integrated correlator in terms of isonance series. Great. Right, so I mentioned earlier that that rational function looks a bit random. However, it obeys certain differential equations. Again, I won't bother you with the detail, but that differential equation eventually leads to differential equations for the integrated correlator. And that I summarized here. So we call it the Laplace difference equation because there's a Laplace operator acting on the integrated correlator, then related that to itself, but also the correlator with one more, so n, and one more less n. So this is a two-step difference equation. I think this is a quite a remarkable difference equation. In particular, it's useful that we know that the G1 is 0 because the correlator for SU1 vanishes. So once G2 is given, well, I almost gave it. Well, in fact, I basically gave it to you because B2 basically tells you what is G2. So once G2 is given, this Laplace difference equation determines U for all the Gn's for all n. In the following, so I will basically study properties of this this integrated correlator in various limits. Okay. So one limit is the weak coupling for arbitrary n, for finite n. So well, here's just list the results, and I use lambda to hold the coupling, so that's a gm squared times n. But so as I said, it's really for finite n, but it's just that the lambda is convenient to combine things together. So a few comments. One is that we proved that one loop and the two loop returns agrees precisely with the known results in the literature. So I mentioned at the beginning of the talk that this unintegrated correlator was known to 3 loops. So what we did is that we took the known results, well, at least 1 loop, a 2 loop, and we integrated over this particular measure I mentioned earlier. And for 1 and 2 loops, we were able to do the integral and find that the result precisely match this. And for the 3 loop guy, in principle, we should do that. But 3 loop, for those who know the story, is a bit much more complicated. So, well, we were not able to do the integral. So we didn't check this case, but it would be great to check this one. And furthermore, of course, the integrand was constructed to 10 loops for the planar one. So namely those ones should match. If I take the 10 loop integrand, integrate over this measure, localization predicts that you should get this particular values at each loop order. Nevertheless, we at this moment, we have only checked 1 loop and 2 loops. That's already highly non-trivial, I should say, because as you may know that the function, when you depend on the space-time or cross ratios, they are non-trivial functions of polylog regions. And magically, when you integrate over that measure, you just get zeta3, zeta5, zeta7, etc. Furthermore, the other fact I mentioned about this correlator is that non-planar contribution starts to end only at 4 loops. Now, as you see that indeed, so that's what we found here. So the first 3 loops, well, except this overall factor, has no end dependence. And the non-planar contribution only starts to end at here. In fact, furthermore, the next order of non-planar contribution only started to end at the 6 loops, not 5 loops. And this pattern goes on. The non-planar contribution to higher loops always end every 2 loops, not every 1 loop. Again, this actually also was observed by others to study form factors. The same pattern was found. So again, it's an agreement with known results. As I kind of mentioned already, so this result obviously gives predictions for all loops of this correlator. So in principle, we could take this 10 loop integrands by Haslope and the correlators, check indeed those right numbers produced from there. Okay, so we studied other limits. In particular, we studied the larger n limit in the small lambda expansion. So this will be the standard say genus expansion. So G is denoting the genus, and from the known result, so we found the 0 genus takes this form, and genus 1 takes this form. So I emphasize here that those theories are in fact convergent with a finite convergent radius at lambda smaller than pi square. So lambda again is a two-hold coupling, and since they're convergent, in fact you can just resum it. And for instance, for the G0, the leading guy, and resummation result is given by here. And this result again in agreement with what was originally computed previously by Binda and the correlators. So again, so we did a lot more high order terms, and again, they are in agreement with results produced by Chester, and we even produce new ones. Okay, things we can do in principle any order we want. The other expansion is that doing larger n expansion, but larger lambda expansion. So from string theory point of view, that will be alpha ply expansion. So again, so you have G0, G1. So G0, G1 is according to the order over n, and this is the result is the leading order, the result the subleading order, and so on. Okay. Now those theories, you probably can see it actually because a lot of gamma in the numerator, they are asymptotic. And furthermore, another way, and they're not the Boole summable, roughly speaking, because there's no alternating sign. So if there's like -1 to the n, that would probably make it Boole summable. However, in this case, they are not Boole summable. Therefore, well, they require a non-predictable completion for those terms, and we computed the non-predictable completion. And in particular, say for the leading guy, we found that the non-predictable completion should take this form. So those are like polylogarithm, and so they go like exponentially e-2 square root of lambda. Now, if we translate it into string language, alpha, so square root of lambda, well, which is like square root of n, which is basically 1 over alpha pi. So I think in the language of string theory, they are the virtual instantons in ADS5 cross S5. So another direction we like to study was to study larger n expansion, but now with finite coupling. That can be done by expanding this rational function called the BNT. So we can do a larger n expansion for this polynomial in larger n, and we found that the result take this actually is quite a simple form. So you see at each order, more or less very symmetric the object appears. So you here at least a few orders, but of course you can go as far as you want. And then we can plug in this integrand into the integral, and we will see that this leads to a larger expansion for the integrated correlators at finite coupling. And turns out all those guys combine together and gives the non-holomorphic Einstein series again. So if you remember, I began with there's a correlator, and I said they can expand in terms of non-holomorphic Einstein series, and there the summation was a summing over integer non-holomorphic Einstein series. Namely, this index S, I probably forgot to emphasize, the index S in the finite n was integers. Now we found that in the larger n expansion, again, the function can be expanded in non-holomorphic Einstein series, but in the half integer. Okay, at each order of 1 over n. So part of this result was already known in our previous paper. So we basically reproduce them. And of course, now we can go as a higher order as we want. Furthermore, when we wrote the first paper, we were kind of puzzled by those numbers, like why those particular numbers appear. Now we understand because those numbers appear such that they satisfy this Laplace difference equation. Said in another way, this result can also be obtained by solving this Laplace difference equations in the order by order in 1 over n expansion. With of course, when you solve the equation, I should input some initial condition. So once we input some initial data, and that will be result out of the Laplace difference equation. So let me make a comparison with type 2B string theory on ADS5 cross S5. So yeah, so the result, let me just remind you. So there's a leading order n squared, then n half, 1 over n half, and so on. So it's basically goes like 1 over n, but each order is, except for the first one, it's a half integer of n. Okay, so the leading order is basically the integrate result of the supergravity term. So namely, to take the supergravity result, integrate over this measure, and that, say 1/4, is supposed to the result you should get. Then the next one is basically take r to the 4 on ADS5 cross S5, and again integrate over that particular measure, and this is the number you're supposed to get, and so on. Another thing one notice is that for this particular integrated correlator, turns like this. In particular, say n=1, which is d6 r to the 4, doesn't appear. Namely, d6 r to the 4, when I integrate it over this choice of measure, gives it to 0. Okay, it's just the fact, and it's fine. So to get a non-zero result for, say, d6 r to the 4 or d10 r to the 4, oh, sorry, it's d10 r to the 4. I don't know why I write that. Sorry, d10 r to the 4. And one should consider, it turns out one should consider the other integrated correlator. You take the partition function and take 4 mass derivative on that. This correlator is slightly more difficult to evaluate, especially at the finite n. One reason is that this simplicity I mentioned about this Young diagrams of the Instanton doesn't happen anymore. In particular, so more general Young diagram will contribute if we try to compute the Instanton contributions. But nevertheless, in this paper, we were able to evaluate this object at least in the larger n expansion to certain orders, and that gives you us say integrate results for, say, d6 r to the 4, d10 r to the 4, and sorry about this, as well as those guys which already appear here. Okay. So now the final point that once you get this integrated correlator, one can actually reconstruct, as I mentioned earlier, the unintegrated correlator, the correlator which has space-time dependence. The idea was that you can write ansatz, well, at least in larger n expansion. So you can write the ansatz for the milling amplitudes, and by understanding, say, the poles or the dimension counting, and the larger n expansion or the milling amplitudes of this 4-point correlator basically should take this form. So the first term is supergravity, and this term is r to the 4. This term is supergravity, at the 1 loop level, and this term is d4 r to the 4. this thing is D6 out of the 4. So D6 basically here just counting. So STU, you can think of number of derivatives. So this will be each S or T and U, they have 2 derivatives. They are like minus non-variables. So therefore, this will be like 6 derivative D6, and this will be like a 4 derivative, and this has a 0 derivative. Yeah, and as I said here. And now knowing so what we now the job left over is basically to fix those unknown coefficients. Okay. For the first 3, well, 1, 2, 3. Well, let me not consider the one loop case. 1, 2, 3. So for the first 3 case, maximally we only have 2 functions to fix, and we do have 2 integrated correlators in the larger N expansion. So one coming from take the partition function, take a derivative with respect to mass, and take a derivative with respect to coupling. The other one is take a derivative with respect to mass 4 times. Okay, with this 2 condition allows us to fix all those unknown functions order by order in 1 over C expansion. In this case, which correspond to D6 out of the 4, now we have 3 functions to fix, and we only have 2 conditions. Indeed, we are not able to do that. However, there's a so-called flat space limit. So namely, so I'm talking here, I'm writing down the amplitudes on ADS5 cross S5. However, you can take a flat space limit. In particular, in that limit, this term will dominate. That should match with the flat space amplitude, which we already know. So now, if we include the flat space limit, then there are 3 conditions for these 3 unknown functions, and we can also fix them. And that's the result I show you at the beginning of the talk. And for those cases, so the flat space limit I mentioned, it can be taken as an independent check, because now, say for this case, I have 3 conditions if I include the flat space limit for 2 unknown functions. And indeed, we find the answer is consistent. Okay, let me conclude. So I discussed this integrate correlators, and I emphasized that they can be computed using supersymmetric localization. So in this talk, I mentioned a bit the other integrated correlators, but mostly I focused on one of them. And for this particular integrated correlators, we can present it as a 2-dimensional lattice sum, and the result is for, again, for arbitrary and arbitrary coupling. And the expression due to this 2-dimensional lattice sum make manifest the SL2Z invariance of this theory and for Supersymetric. And for this particular integrated correlator, it obeys a Laplace difference equation that relates the correlator of SUN theory with those of SUN plus 1 and SUN minus 1. And particularly, once the correlator of SU2 is given, one can determine the correlator for arbitrary n. And then I studied various limits of this correlator. I studied the small GRMUS expansion for finite n. That basically is a loop expansion. And we checked that the results are consistent with known results in the literature from more standard perturbation computation. And we also studied large N expansion with a small and large lambda expansion, in particular emphasizing the convergent property of this expansion. So in the case of small lambda expansion, the perturbation theory is convergent with a finite radius, and the large lambda expansion is not convergent and even not Boole-summable, and requires a Virtual Instanton completion. Finally, I discussed large N expansion at finite coupling, finite tau, and this result was matched with the known, well, in the flat space was known, matching with the string amplitudes on ADS5 cross S5. So maybe some future directions. Well, so I have emphasized we will this formula was guessed or conjectured by studying huge amount of examples and found the pattern. Clearly, it would be interesting to prove it, and I believe that proving it will let us understand better, say, where this formula came from. This two-dimensional lattice sum may have something to do with, I don't know, two-dimensional worksheet. Anyway, for whatever reason, proving this directly or rigorously should be interesting. The other clear direction is that we should try to generalize for other type of integrated correlators, in particular, let's say for mass derivative on the partition function. And I already said that in the larger n expansion, the answer was known, at least for the very first several orders, and the answer was known. And in the larger n expansion, the answer was given by so-called generalized non-holomorphic Einstein series. So in particular, whatever final result should reproduce this larger n expansion. And said in another way, this larger n expansion result maybe give hints what it should be at the finite n. Another probably interesting direction. So here we just talked about the 4-point correlator. It would be interesting to extend this story, say, for higher point correlators, especially those that we call so-called maximally U1 violating correlator, or other people may call the Maxwell neopotent correlator. And those are the objects associated with so-called modular forms. So, say, non-holomorphic Einstein series are called modular functions in the sense that they are invariant under SL2Z transformation. And for those objects which has a non-trivial so-called U1, they transform non-trivially under SL2Z, and they call it modular forms. It would be very interesting to extend the story for those guys. Finally, well, not yet finally. So here I discussed the 4-point correlators for the lowest weight. So I call it O2, namely they have conformal dimension 2. But clearly, it would be interesting to extend study the correlators with higher weights. And in fact, it was talked last week by Heslop. That was interesting so-called hidden relations between those high weight operators or correlated or high weight operators with the lower weight ones. Well, at least, well, first it was discovered at supergravity limit. Then there was some extension, even you include string collections. So it would be interesting to see if there's any hint, even for the integrated correlators. Finally, so we have been using techniques of supersymmetric localization. However, some of the answers we found kind of more or less have a hint, may have something to do with integrability, although, as I emphasized, we are talking about the finite n, not the planar limit. And on the other hand, say, those larger n limits, such as the convergence of the theory at the small lambda and the non-Boole-Sanger-Boole at the large lambda, and in fact, the people already saw in the study of the Kaspar's anomaly dimension in enforceable Yamir's. So, and that study comes out from integrability. Maybe these things are connect to each other. It would be interesting if there's such connection. So let me thank you again for for everyone to come in, and let me finish here. Thanks.
Thank you. Okay, are there any questions?
So connection to integrability maybe just comes from the fact of that localization is an integral plus Instanton contributions, which may have some hidden integrability in this integral, in this sum. It may not be the same one which is in the planar limit.
Yeah, maybe. Yeah, or I was saying that like for instance, this sinh function. I don't know if I have it here. Yeah, for instance, this integral representation like this sinh somehow also appears in the Casper's normal dimension. I don't know, may or may not as a hint, but similar objects appear. Yeah.
Hey, Congkao.
Hey, Sinan.
So I have a question. How do you compute these integrated correlators for higher weight operators? I thought like the localization method only works for like 2, 2, 2, 2 and stuff.
Right. Yeah. So indeed. So for the non-instanton part, just for the perturbation part, so in the original paper, they did a study for higher weights ones. And so indeed, so if we try to, well, the point that if we want to compute a higher weight, you have to insert the higher weight operators and take the derivative. And then the question is, when I insert the higher weight operators, I have to do localization for higher weight operators. So one has to go through the whole procedure of localization, then I inserted the higher weight operators. In the perturbation, in the first paper, they did compute the high weight, I think a PPQQ or maybe 22PP, but there is some high weight operator was involved. But you are right. So if I want to complete the story, namely including instantons, indeed. So at this moment, there was no known procedure of how to do that.
Thanks.
Yeah, thank you.
Can you like briefly say what's the origin of this difference Laplace equation?
Right. So let me find it. Yeah, origin in the deeper sense, I don't know. Maybe I don't know. Michael or Daniel can comment. But you know, from the superficial order, was that well, we know the correlator can be written in this way, and we know explicitly what is B. Well, what we do is just that we act on the correlator with this operator. And so act on here, there's some differential operator act on this side, and that will pass through this and eventually act on B and use the probability of B. Then we can derive that differential operator. So that differential Laplace difference equation. So said in another way, this is the equation we found after we know the correlator written as this form. So yeah, the deeper meaning, yeah, I don't know. I don't know.
Mm-hmm.
Yeah.
Okay, thank you.
Yeah, in the larger N expansion, so I probably didn't discuss that. Those functions, so-called non-holomorph isomorphic, they obey, well, not exactly this, but they obey certain Laplace differential equations. Sorry, not Laplace differential, they obey Laplace equations, because order by order for each non-holomorph isomorphic. So again, for those functions, it's a standard to take this Laplace operator, act on them, and give you eigenvalue. This, in some sense, is a generalization for for a given order in large N, say leading order. It's so-called E3 half, and that non-homomorphic essentially obey a Laplace equation, say tau square d tau bar, acting that equal to say 3/4 with eigenvalue 3/4. So this one, in some sense, is a generalization of that now involving M. One may also say write this difference equation as a differential operator acting on N. So, well, it's not hard to imagine that. And that, say, in particular, this will become, there's a shift on N. You can write out, all the shift, you can write the exponential derivative on N. So this kind of generalizing the simple Laplacian operator I mentioned earlier now involves the N. That's how you make a connection for the correlators of different N. But again, a deeper aspect of this equation, yeah, I don't know.
Okay, thank you. Are there any other questions? Okay, since we don't have other questions, thank you for a nice talk. And thank you everyone for coming.
Thanks. Bye-bye.
Thank you.